Okay, welcome for coming back on the last day. Today we will harvest what we have planted the first 2 sessions, and we'll do all the cool stuff that you haven't seen yet. We've made it to Friday. Actually, we're still in the start on Wednesday, so today we're going to do the end of probabilistic inference, and then in a combined effort we will do learning conditional random fields, map prediction, anonymization, and learning structured support vector machines. And because that sounds like a bit too much, I cut out some of the best parts. So I will put the slides online with all the material, but I will leave out some parts that would be too much going into detail for today. Unfortunately, that contains also the part about deep learning. So if you're interested in how graphical models and deep learning can be combined, not that there is so much so far, but if you're interested in what is there, you will have to look at the online resources at some other time. Sorry about that. So today we're going to continue on inference and learning. And just to remind you, we will work with vector graphs. Vector graphs, this was these graphs on the right, which are bipartite graphs of little black squares and round circles. The round circles are random variables, and the black squares indicate a term that shows up when you write the probability distribution of that vector graph as a product. So you know that the final distribution, in this case over the random variable y, which decomposes into a lot of parts, one per graph node, will factorize into a product. There's one term in the product per factor, which are the little black dots, and each factor takes only a subset of the random variables as input, and that is the ones that it's connected to. So the one on the top right, this guy is a function that has 2 arguments, these 2. This is a function of just 1 argument, and so on. The final distribution can be written as a product of all of these factors, up to a normalizing constant that we will need in order to make the whole thing sum up to 1. The normalizing constant you can compute by just taking the unnormalized thing, the product over the factors phi, or psi here, and summing up over all possible configurations y, and that way you've computed a number such that when you afterwards multiply the entries of, sum the entries of y, it will add up exactly to 1. So that's how we construct a distribution from a factor graph and vice versa. Last time I skipped over this a little bit too quickly, so here we describe the distribution over all random variables, yi, yj, and so on. So we can also use this to only characterize a conditional distribution, where some of the random variables are, well, we care about the distributions, but some of the variables are fixed to a number, so we don't have to care what the distribution is because we observe them anyway. So, we also introduced this notation of energy, right? So we said that the product over the size, we can also write as exponential of the sum over energies, where the energies are the negative logarithms of the factors. That is sometimes convenient to write. Okay, so if you want to model conditional distributions, well, we have essentially that every factor that is connected to a shaded x node, that means there's another value in the x which is fixed. We don't need its distribution, but we need its value. So that means the factor becomes a function of that shaded thing as well. But it only describes the distribution about the y's, so only about the unshaded thing. So what we will have is we will have a function that is a product of the factors. The factors are a function of the y's and the x's. The x's are fixed. What comes out will be a distribution over y for any fixed value of x. So it's a conditional distribution of y given x. And the one thing that changes is if you sum up these things, the outcome, the normalization constant, can still depend on x, because we sum over all y's, but for different values of x's there could be different outcomes. So the partition function, the normalizing constant, can be a different one for every value of x. It's something to keep in mind. So it's still constant with respect to the y's, which are our objects of interest at the moment, but it does depend on whatever input we currently try to predict on. And this is the setting that is called the conditional random field. We model a conditional distribution using a Markov random field, basically, or a Markov network, as we call them as well. Okay, so now let's return to the task that we did so far, and that was estimate the probability of parts of the variables, or all of the variables, given some input. So what we saw was you can compute, for example, the partition function for any fixed x, or the marginal probabilities of one of the variables and all the others gone. Using probabilistic inference, and the first thing we saw was belief propagation, which was this method of computing subparts, summing them out, matrix vector multiplication essentially, sending these messages to other variables, summing them over there, sending it on, and so on. And we also saw that this works for trees and for chains. If you want to do it for graphs with loops, you have to do some tricks because you don't, usually you need an order of root to, of leaf to root. And if there is no leaf and root, then you cannot call it. You might have to do some trick like the junction tree that takes a complex graph and makes it into a smaller one of bigger nodes, which isn't always efficient. All these three compute the exactly right marginals, meaning what comes out of the algorithm is the correct probability of a state given the input. So under the model, it produces the correct values for this model. Sometimes that is not possible. Sometimes we have to do approximate inference. So I'm going to tell you a little bit about how we do that and what its properties are. So the first thing you could do is if you have a graph with cycles like that, maybe you're a big fan of belief propagation, maybe you want to run belief propagation even though the graph is cycles. So the main problem you have is not how to do it because you know these update rules, but you don't know where to start and where to end because you don't have a root and you don't have leaves. Right? So what do you do? Well, people said if we don't have a loop, we don't have a particular order, we just do it everywhere in parallel at the same time. So we start everywhere and we propagate to everywhere. So loopy belief propagation is a very simple thing. You start with these message vectors at every variable and set them to constant 1 or any kind of constant you want. And then you use the rules of belief propagation, meaning take the values at a certain variable, sum them up, propagate them to a factor. At the factor, you multiply the function of the factor with the vector that came in, propagate it to the next, and so on. So these update rules you apply to all nodes in parallel, just moving vectors of messages around and around and around. They can go in circles and so on, until a stopping criterion is reached. So it's the naive way of doing the same thing, even though it might not be very justified, but the implementation didn't change at all. So what's going to happen is, well, you don't know. It might or might not converge. Often it does converge to something, so that ultimately the messages change less and less, and eventually they don't change anymore. But it is possible that you get some kind of oscillations or cycles where messages go up and down continuously over time. Even if it does converge, there's no guarantee that what you get out is the true probabilities of the states you care about. It's only an approximation, and you do not have any kind of guarantee that this is a consistent estimator or these things that we talked about. It's just a number, and we have to hope for the best. There's some things that fix it. There's some convergent variants which guarantee to converge, but they will still be approximate. They will not give you the right thing. And that is not overly surprising. You can study this from a complexity theory point of view, and it will tell you that computing these marginal probabilities of random variables exactly is sharp P hard. And if you don't know complexity theory like you can look it up. And I found that sharp P is the complexity class that is the counting analog of NP hard. So NP is about decision problems. Does something have a hallucination, yes or no? Sharp P is about counting them, so how many answers does it have? So it's not easier than deciding, it's at least as hard, but it's a different complexity class. Summary, it's hard. Don't expect to find a universal algorithm that solves all of them efficiently, because that would prove a lot of things that we don't think is true. So this looks like a horrible algorithm, right? I mean, it has really no guarantee whatsoever, except that it's easy to implement. It's still surprisingly popular. So people use it, and often they get good results. It's just, if they don't get, they try. If they don't get good results, they use something else. But if they do get good results, they stick to it. What else could you do? There's a very big branch of approximate inference that works by sampling. So it's based on the observation that what we want to do is we want to compute the marginal probabilities of a certain variable. That is the same as computing the expected value of an indicator. So if you compute the probability of something having the state 5, it's the same as the expected value of the function that is 1 if it has the value 5 and 0 otherwise. So you can write expectations, you can write this kind of probability of states also in expectations of a function. And that is nice because expectations of functions you can compute by sampling. So you create samples from your distribution. Ideally they are independent and identically distributed. That's called y1 with upper indices, 1, 2, 3, and so on. And then we know that the expectation of any function under that distribution can be written as some estimate, and the estimate is just you evaluate the function on the samples, and then you sum it up, or you average over all instances that you have. The nice thing is, this is actually a consistent estimator, so if on expectation over all data, this will give you the right thing. And the law of large number will guarantee that it converges. The more samples you've seen, the smaller the variance of your estimate will get, and it will converge to the true value in the limit. So if you can afford a lot of samples, you can compute all the quantities exactly. The disadvantage is, well, first you need to get samples from your distribution, and if these should be independent samples, it is a very hard task to achieve. It's not clear how you create independent samples from these kind of loopy graphical models. For the belief networks we saw, that was easy. We had this kind of direction from root to leaves. We started with sampling a state for the sprinkler, then we sample a state conditioned on the previous for the next, and so on. From this directed models, it's often easy to sample, the generative models. For these models where you have no order of variables and everything depends on everything, it's hard to sample. So we don't know how to do that in general to create independent samples easily. There is a certain solution to that, and that is the law of large number and this unbiased estimator property hold not just for independent samples but also for dependent samples. So if you have a sequence of samples that depend on each other, they have in general the right distribution, but they are not completely independent between two samples. This will still hold. The law of large number will still tell you that the variance goes down. It just doesn't converge as quickly as it would for independent samples. And creating dependent samples, a sequence of dependent samples, is actually quite doable for these graphical models. And that is what's underlying the Monte Carlo Markov chain technique. So there's whole books and lectures about that. Let me just give you one example of how such a method for creating samples could look like. So it's a very famous method called Gibbs sampling, and it works this following way. You start with an arbitrary configuration of labels. Let's set them all to 5 or 0 or something. That's not a good sample yet. And then you iteratively go for as many samples as you want. You select an index I, so that is one of the random variables that we want. And then you resample it based on its true distribution under the model, conditioned on all the others. So if you look at this in the picture, it would be, this is the variable we picked. So it's not shaded, it's the one we actually care about at the moment. We fix all the others to a value, so we make them all gray. That means they're all just values, we don't care about their distribution. And then this in the end is a distribution over just one variable. We sample from it, typically sampling from one variable at a time is doable. And then we get a new output sample, which is everywhere the old one. We keep ys for all the positions, except for the one where we sample the new entry. So we just replace the existing, in one location we replace the value with a new sampled value. Now clearly this is not independent of the previous, so the ys plus 1 is not independent of the ys because it's almost identical everywhere. But if you run this long enough, eventually everything will change, and you will see that this is a Markov chain that has, as the stationary distribution, the correct distribution, which means if you sample from this and average over the samples, it will converge to the right estimate. So it's a very easy procedure for sampling dependent samples that actually in the limit converges to the right thing. We should say that sampling from this guy is easy because if you do the math, what do we need? We need the conditional distribution of one variable given all the others. And in this model, if you condition on a lot of stuff, things get easier. So we can plug in what that means. What is the conditional distribution of one given all the others? Well, it's the joint distribution of all of them divided by the joint distribution of just some of them. I mean, all but one. How do we get the joint distribution of all but one? We take the distribution over all and marginalize out the one that we don't want at the moment. This is a one-dimensional summation. We just sum over all values here. Now we know that this probability is 1 over a partition function. We cannot compute this probability, right? We don't know the partition function. But we know that it's 1 over the partition function times the exponential of some energy, and the energy is something we can compute. And the bottom is the same. We sum over the states of partition function e to the minus energy. And now the magical thing of all of these sampling techniques, the MCMC, is that the partition functions will cancel out in numerator and denominator. So we don't need to know what the partition function z of x is, because it cancels out anyway. So what we are left with is we can compute the distribution of one variable conditioned on all the others by just evaluating the function, which is the energy once on the configuration we know, and dividing by sum, where we sum over as many states as we have in this variable. But typically, summing over one variable at a time is doable, because otherwise, if the state space of one variable is too big to sum, then we are pretty much out of luck for anything. So if you cannot handle one variable at a time, then you put the wrong problem to start. So sampling from a conditional distribution of just everything except one is easy, but the marginal distribution is the hard one, and for that we do this dependent sample trick. Typically, since we start with a fixed value, which is not any kind of related to the distribution, you wouldn't use all samples you produce with this, but you would start creating them. Then you would wait for maybe 100,000 samples, throw all of them away, and then only afterwards you really use the samples for the averages. Because it's called a burn-in period, where in the beginning it's not still adjusting to the procedure, but then after a while it has found the stationary distribution and you get good samples. And that way it will not matter how you initialize the first sample. You just take anything that comes to your mind. After you've done that, already switched variables, that's good. Okay. The last thing, which is also a whole field in itself, is variational inference and the special case mean field. Again, the task is to compute probability for some of the variables, and it's based on the idea, well, the simple idea that it's hard to compute probabilities of this type from a hard distribution that has this kind of loopy structure. It would be much easier to compute the marginal probabilities of anything if we had an easier structure like the one in the middle, which is a tree, so we know that we can run belief propagation, or even the one on the right, where everything is independent of each other, so we can read off the probability of any variable just from the local variable without any interactions. So the idea of mean field is that for any distribution we have, maybe we can approximate the current distribution, which is the p of y given x. We can approximate it with a simpler one that is similar in the sense of Kullback-Leibler divergence. So we find a new distribution Q star, which is as close as possible in the sense of Kullback-Leibler divergence to the one we actually care about. And the one we approximate, we choose from a simpler class. For example, we choose it only from these kind of tree models. And then we choose the one that is best, and we hope that if the distributions are similar in KL divergence sense, then they also have similar marginal probabilities. So we compute for the easy distribution what the probabilities are, and then pretend that these were the ones for the original. There's some theory for this. You can prove some kind of bounds on what the approximation really does, like bounds that the partition function so it's always a lower bound to the true partition function, or upper bound, one of the two. But ultimately, in particular, it's an easy technique for reusing things that you already can do, like inference on trees, also in order to do it for non-trees. So there's no closed form solution how you do this closest approximation. But you can derive some kind of, if you would have found the optimal distribution, certain conditions hold. In particular, you would get that the optimal distribution Q, if you look at a factorizing product that is just a product of individual terms, the optimal Qi has to be proportional to the exponential of the expected value of the energy under the other distributions. That by itself doesn't tell you how to set it, but you can come up with an iterative scheme where you start with your estimate of Q somewhere, and then you go through all the entries of Q, and every time you update its value based on this expression up there. So you compute the expected value of the other variables given that one, and so on. So you get an iterative update techniques that ultimately more or less converges to the right thing. Again, there's no guarantee that this gives you the exact thing, but if you don't know what else to do, it's something that is worth trying. In particular, it has become very successful recently with convolutional networks. So if you work on image segmentation, you might have seen that convolutional networks, deep learning, produce some kind of segmentation masks. So, but they look like the top right. So they are more like blurred heat maps that tell you the object is roughly here. So if you scale them up to full resolution, well, they're still very blurred. But then if you use the output here as factors in a graphical model which is fully connected between pixels with certain weights, and then you compute this kind of mean field type approximation in order to compute marginal probabilities, you will actually get a better output than from the original bilinear. So the visualization that was in the original papers, you start with some input, you get relatively blurry outputs. These are the potential function we plug into the conditional random field as functions that depend on the location and the image. And then you do this mean field to find a better distribution per pixel. And after a few iterations of this mean field updates, you get a nice and crisp segmentation, which hopefully is similar to your ground truth.
So why does mean field work so nice in this application?
Mean field often works pretty nice. In particular, it is a nice technique. Mean field, the name also comes from physics, where the idea is that if you have a particle that has a lot of interactions with other particles, like a gravity, one particle in lots of gravity, then ultimately what matters is not the individual interaction anymore, but just the average. So you replace all the individual particles with like the average at that location. And that is exactly also what this expression tells you. So you basically average out over all the individual others. And for the segmentation example, that's more or less also what happens. You have a network that has many connections to lots of other pixels. And instead of saying, I look at the connection of each pixel to every other pixel separately, I more or less replace your value with your average of your neighbors. And as this is set up, you don't do the average of all your neighbors, but just of the neighbors that look similar. So a pixel here would get as label the average of all the labels of pixels that are also this kind of blue. And since most of them are dark background, it would get background. A pixel in the wing would get the average label of all pixels that are dark. So it would get the average of all the things that look like planes. And then a single jump from one pixel here to one pixel there will change which neighbors interact with you. So you might get a sharp boundary. That's my interpretation of things. Other people might think it's different, but it works. Okay, so and there's other ways of doing probabilistic inference, but these are like the main categories. You either create samples and compute statistics from them, or you do this message passing stuff, or you do approximations of your distribution by simpler distributions. And it doesn't have to be a product per term. It can be a mixture of all kinds of trees and so on. So you have a lot of freedom in how to design them. Okay, so that's a summary of probabilistic inference. There's exact probabilistic inference, which is only for a small class of, at least efficiency works only for a small class of models. And there is approximate inference methods, the three I mentioned, and lots of variants of them. And there's really no one to rule them all kind of methods. So you have to understand your model, maybe try different methods, and see which ones give you, which characteristics of your model you can use in order to do inference efficiently. Sometimes the best is to just not rely on them and to choose a simpler model. So there's always design choices involved. Okay, so is there questions about computing probabilities this way. Good. Then let's come back to prediction. So now we really have all the tools available that we need in order to learn from data a structured prediction problem. We know how to set up a model of a probability. We know how to fit its parameters, at least in some situation, namely if there are discrete tables. We know what to do. Okay. We know what to do if you have a fixed model and you want to make a prediction. What is the best prediction to use? So the only thing that's still missing is actually doing that and a little bit of parameter learning for models that are not just probability tables. So we're going to do that. We're going to assume that we have given some training examples, x and y, where x is the input and y is the output that we want. We assume them structured, like here these poses. Green is basically the y that we want to predict. Here it's given to us as training set, but for new data we want to predict it. And x is the whole image from which we want to predict it. So how can we learn a function from x to y now? There's three approaches at least. Some of them we've already seen. In the very beginning, we looked at generative models where we would get the training data and try to get an estimate of the joint probability of x and y. And then once we have that, we can use the rule we derived for loss optimal prediction. Right? Choose the distribution that has the smallest expected loss under the model distribution. The second one works exactly the same, except that we do not model the probability of x and y jointly, but only of y given x. So only for the fixed x's, only for treating x as a fixed object, not as a random object. Still, we know how to do optimal prediction by minimizing the expected loss. And the last one we're going to talk about at the very end is loss minimizing prediction, where we do not model the probability, we directly learn an energy function from the data, and we minimize this energy function to make predictions, and we'll see then how that can make sense if we do not have probabilities to work with. In fact, I'm not going to talk about the first one because it's difficult. I'm going to talk about the second one where the first is very similar, and I'm going to talk about the third if we still have time. Okay, so this part is conditional random field learning. I'm not sure it's number 5, but it's the part we're going to have now. And you can summarize it as given a parametric model of the outputs, given the inputs, and the parameter, maximize the probability over the possible parameters. So it's maximum likelihood training of a conditional random field. So that's what we're going to do. We just write it down again, given some training samples. What we really want is to learn the posterior probability that is most likely, so y given x. And it's going to be a partition function, 1 over z of x, and the exponential of the sum of these factor terms. And we can choose any kind of parameterization for these factors we want. One thing we need is we will be able to evaluate this energy and thereby the probability for all possible values of x. Not just for the ones in the training set, then we would just memorize it, but we also need to be able to take a new x and plug it in there and evaluate and get a distribution out for that. So that means these energies have to be a function of our data somehow that we can evaluate on arbitrary x's. And what we're going to do is we're going to parameterize them, and the easiest parameterization is as a linear function. So we're going to assume that each of these energies is a linear function, which I write as an inner product. So these pointy brackets is inner product. We treat some feature vector that we can compute, and we compute it from all the information we have. Each factor depends on some of the unknown labels, and if we want all of the input data. So the features will also characterize the unknown y's that we care about, and potentially all of the input data. So this gives us a vector of features, and then the w is a weight vector that is multiplied to this, such that as an inner product we get a number out, and in the end the energy is a number for every configuration of the y's and x's. Each of these energy terms gives us a feature vector. If we stack all these feature vectors after the other, we get a much longer feature vector, and that we call phi of x and y. So that is the representation of an input and an output together as a long vector, which we will then use in order to predict scores. The same way we're going to take our weight vectors, stack them one after the other. That gives us a really, really long weight vector. And together,
the sum of these energies that we have to compute is just the inner product of the concatenated feature vectors with the concatenated weight vectors. That's how the inner product works. So as a result, what we'll get, we get a model for the conditional probability of our outputs conditioned on the inputs and the weight vector parameter. And this will be the exponential of a big inner product between a weight vector and a feature vector that now looks, just for convenience of writing, it's a function of everything we have, so the outputs and the inputs, with the normalizing constant in front. And the normalizing constant now depends not only on the w, but not only on the x, but also on the w, because for every value of w, this has to be a distribution. So everything in this is specified, x, y, exponential, and so on, how we compute the z, but what we don't know is the value of w. We assume that the feature is a fixed feature function, but the value of w is our unknown in this parameter. So it's the parameterization that we want to learn from data, as we saw for the previous examples of learning. So learning a conditional random field means finding the parameter w in this representation that maximizes the probability. So it's maximum likelihood learning. What's the best parameter? The parameter w star is the one that out of all possible parameters w achieves the highest probability of the observed outputs given the observed inputs. And since our data is independent, that turns into a product of the individual probabilities of seeing a certain output given an input. And with the usual trick of taking minus logarithm, that is the same as minimizing the negative of the conditional log likelihood instead of maximizing likelihood. So this is the same steps we did for maximum likelihood learning. We can massage these terms a little further because we know what this p looks like, right? The p is 1 over normalizing constant times exponential of an energy, minus an energy. So we can plug that in, and we use the rules of the logarithm. So then the p is logarithm divided, or exponential divided by a constant. This is logarithm of the exponential minus logarithm of the constant. But logarithm of exponential of this inner product is just the inner product itself. And the second term, logarithm of the normalizing constant, well, there's not much we can do. We can just write it the way it is. So what is the normalizing constant? It's the sum over all possible labelings of this exponential term that was the unnormalized part of the distribution. So the first one is just the energy, negative of the energy of a training data. And the second one is the so-called log partition function. It's the logarithm over this gigantic sum of all as many things as we have. Okay, we just manipulated the terms, and this is now the optimization function we have to solve. The alternative, as we had last time, is we can, instead of maximum likelihood, we could do map estimation. We could compute the posterior probability of our weight vector given the data, and then find the maximum value of that instead of the maximum value of the data likelihood. If we do the steps, it's the same steps as we had done before. We have the probability of any weight vector given the observed data by Bayes' rule can be written as the probability of the observed data given the weight vector multiplied with the prior of the weight vector normalized by the probability of the data itself. This decomposes into a product. Now, if we want to maximize this over all possible weight vectors, the same as minimizing its logarithm. We again know what the form of this W given D has this form here, right here. So we plug that in and use the rules of the logarithm, and we end up with the same rule that we had for maximum a posteriori learning of general parameters. It will be the sum of the log likelihoods, here conditional distributions, conditional log likelihoods, and the logarithm of the prior itself, which tells us which weight vectors we prefer over others. What should we put as a prior over weight vectors? There's several choices. They have different properties. The most common would be, well, we don't care which weight vector is really the best. Yes? Absolutely.
Why does this term independent of weight?
This is the one that is that comes out of here, right? That's the probability of the data independent of W. That means
it contains the integration of all possible ways.
yes, it would be. So this one we can also only compute by doing the joint probability of the data and the weights, and then integrating over all the weights. I mean, in practice we cannot do that, but we know that after integrating over the weights, it doesn't depend on the particular choice anymore. Right? So this is a constant, and it's not a constant that depends on W, so we can drop it for the sake of optimization. Okay. We also have dropped it here already and said that this doesn't depend on W, so it's not. It doesn't matter that what we divide by. Okay. So one choice of prior for W. Let's make it constant. All weight vectors are equally likely. I mean, that might not be a distribution if your weight vector is all of RD, but we can just say, well, it's just in a certain ball region or so. Then this is a proper distribution, and it will just tell us that the optimal weight vector is obtained by minimizing the negative conditional log likelihood plus a constant. The constant doesn't matter for optimization, so it will be the same as the maximum likelihood solution. More common is that we assume certain knowledge about our weight vector. And one thing that has come out over the decades of machine learning is that short weight vectors are typically better than long weight vectors. So long vectors tend to overfit, short weight vectors tend to work better. So let's prefer short vectors over long vectors, or let's assume that if we look for a good one, short ones are more likely to be good. So we put a distribution that prefers short vectors over long vectors, for example, a Gaussian. So the Gaussian has higher values if the norm of the weight vector is small than if the norm of the weight vector is large. If we put that as a prior into our optimization, we get that the negative logarithm of this is the norm of the weight vector itself. So we get that in order to find the optimal weight vector, we have to minimize the log likelihood of the data, negative of that, plus the norm of the weight vector. So in the end, if we minimize this, we will try to get the weight vector as short as possible as well. And this is the so-called regularized negative log likelihood. If you know about support vector machines and regularization, it's exactly the same that happens there. By adding a norm of the weight vector to your objective, you prevent overfitting and prefer more smooth solutions. You can choose other priors on the weight vector. You can choose an L1 norm that will enforce sparsity in the vector. You can do any kind of, if you have any prior knowledge about your parameters, you can plug it in here. Okay, so that means the objective we ultimately have to solve, the negative log likelihood, curly L that we call it, it will be a sum of the potentially norm of the weight vector. If we set the lambda coefficients, which was in the exponential of the Gaussian, to 0, this term disappears and we go back to the original maximum likelihood. So this is the more general version. And then a sum over all examples we've seen, n equals 1 to n, of one term that is easy. It's just the linear term, inner product of our weight vector with the feature vector that we compute for our data, plus a term that is the logarithm over the sum over all states of the exponential of this. Parameter estimation, conditional random field training means compute this value, minimize this function numerically. That's all. In fact, if you took a pattern recognition course or any other course, this objective should look very familiar to you. It's exactly the same as in logistic regression. So logistic regression also minimizes the conditional log likelihood of the data. The only difference is that you try to predict a number and not a structured object, but the functional form is the same. So how do we minimize these kind of functions? Here's some example plots of their level sets. So this is meant to look, okay, maybe you can see something. So this is the level sets of your function, meaning along these lines, the function is constant. Now it's a toy example with just 2 dimensions. So your weight vector is 2-dimensional. You're looking for the minimum, which happens to be here. And, well, outwards, it goes nice and up. This is where the very strong term in front of the weight vector, so a strong regularization. If you reduce the term of that and you keep only the second term, which is the losses and so on, it will start to get more and more asymmetric. So here the lambda parameter in front of the lambda is smaller, even smaller. And if it goes to 0, you might get almost linear stuff or very, very degenerate stuff. If you have a really, really large lambda, well, the lambda term is quadratic. So This looks almost like a quadratic function on the left. So how do you solve these things? Easiest idea in the world. Everybody has seen and used it. Sorry? How do? Any numerical? Yeah, which one? Yay, gradient descent. Thank you. No, too difficult. Steepest descent minimization. Just gradient descent, first order. Never fails. Well, almost never. I'm sure you've seen it, but here's the algorithm, the complete algorithm. You start with an initialization, for example, 0, and then you repeat until you're happy. You compute the gradient of your function with respect to w at the current location. In this case, you do a line search. You say, if I look in the one-dimensional direction of my gradient, where is the function the smallest? That's a one-dimensional search, so I can actually do it more or less efficiently in practice. That gives me a certain step size. How far should I go along my gradient direction? Actually, it's the negative of the gradient we want to minimize. And then we update our weight vector by subtracting that amount of gradient direction from the current estimate. We go back. Eventually, we are at the minimum, and the gradient of the function will be 0 at the minimum. And then this criterion will tell you, well, the gradient is small. We are at the minimum. We stop our iteration. There's, of course, better and more fancy versions. One that is actually very popular is LBFGS for conditional random field. It's an approximation to a second-order method. Second-order methods themselves are not so popular because often you have very high-dimensional features, and then you would need a Hessian matrix, which is very, very big. So if you have million-dimensional features, you can compute the gradient, but a million-by-million matrix might be too much to store and invert. Conjugate gradient works surprisingly well if you know how to do it. Ultimately, this is the easier part. It's a convex optimization problem, as we'll see. So it's very well explored in the optimization literature. One thing to keep in mind is that we do have to compute the gradient of L. There's no of these gradient descent methods that works without computing this gradient. Okay, so here's a toy example how it works. We start anywhere, for example, here. We look at the gradient direction. The gradient is orthogonal to the level sets and points to where the function gets bigger. This is the opposite direction of the gradient. This is where we search for a new solution. We find the minimum along that line. It happens to be here. We compute the new gradient at that location. It points orthogonally from the level set outside. We look in the opposite direction. We find the best spot. We go in the opposite direction. Oops, and we would have been almost there. So if you have a nice smooth function like this one that has more or less roundish quadratic shape, it can work very quickly. If you have a very wiggly or more steep function, it might not. It might take a lot of steps to converge. That depends on your data. Okay, so let's look a little bit more in detail. What does that mean? The first observation is that this function is continuous. That's good. It's differentiable. That is also good. And yeah, without these things, you should not try to use gradient descent. The next thing we can look at is the gradient itself. So this is the gradient itself. And you can see it helps to have one interpretation. And that is, so if you look at the gradient and you think of the maximum likelihood case where the lambda is 0, when would this gradient disappear? When would you be exactly at the minimum? Well, it's the difference of terms. If the difference is 0, you would have 0 gradient. So one way to achieve that is if your expectation on the right-hand side, so that's the expectation of your feature vector under the current distribution, if that is equal to the features you observe, averaged over all training data, then your gradient would vanish. So you would be at the minimum, hopefully. So that means we want to find a model distribution, P of y given x, such that when we compute the expectation of features according to our model, we end up with the observed ones. That kind of makes sense. We explain our data well if the the feature we see in the training data and the features that our models predict to happen are the same. What are these features? I didn't talk about them at all so far. That's because they are really problem dependent. So you can, for any different problem, you can set up a different feature. For example, if you do image segmentation, a typical feature that looks at one location at a time could be if it's foreground or background. So the expectation of this feature under the distribution is how likely is it on average across all points to be foreground or background. So that's like the foreground ratio. And if the foreground ratio you predict by your model is the same as the foreground ratio you observe in your training data, that's a good thing, right? You somehow matched the correct statistics. Okay. Finally, let's look at the second derivative, so the matrix, the Hessian matrix. As I said, this is a big matrix. You wouldn't compute it numerically, but we can write down the expression. And with some linear algebra, you will see that it's a multiple of the identity matrix plus the expectation of an outer product of the feature vector with itself. And the one on the right-hand side inside the curly brackets is a positive definite matrix. It's rank 1, but it's non-negative. If we take a linear combination, or here convex combination of a lot of positive definite matrices, each of these is positive definite. We take for each possible y, we have 1, but if we take the expectation, it's a positively valued linear combination. The result is still a positive definite matrix. If we add a little bit of diagonal to that, or identity matrix, it stays positive definite. So what we get in the end is that the Hessian matrix is a positive definite matrix, or semi-definite included. And that means if we have a differentiable functions where the Hessian matrix is positively definite everywhere, that the original function was convex. That is a nice thing to have. Convex functions are good because convex functions are known that they cannot have local minima except for the global one. So when you find a local minimum of a convex function, you know that you found the global minimum. And that's a good thing. So in our plots of the level sets, we saw there was one spot where the function was minimal. That wasn't a coincidence. These likelihoods are always like there's only one global minimum, and gradient descent will find it. So this is good. One of the few things in graphical models which really, are set up so well that everything works, right? Belief propagation sometimes messes up, but this convex, no local minima, gradient descent works. Okay, so that's the summary of probabilistic conditional random field training part 1. We have a log linear function with this linear term plus exponential of something. Logarithm of sum of exponential of something. Minimizing that numerically is actually a feasible task in principle. It's a differentiable function. It's a convex function. Gradient descent will find the global optimum. And in fact, it's the same structure as in logistic regression, which you find in every textbook of pattern recognition. In fact, if you would be in logistic regression, this is where the textbook ends. It would say, do it numerically. That's it. For conditional random fields, we're not completely finished. Let's have a short break. 6 minutes, 7.